Hello. Hello. Check, check, check. Okay, okay, we'll get started right away since it is already 3:05. So 5 minutes into the session. So welcome everyone to week 3 of this TSF session. Once again, just adjustment. Yeah. So welcome everyone to week 3 of this TA session for this course, Optical Microscopy, Optical Spectroscopy and Microscopy, Fundamentals of Optical Measurements and Instrumentation. So my name is Arjun, and once again, to introduce me, I'm the teaching assistant for this course, and welcome everyone once again to week 3 of this course, of this 12-week course. So to give a short introduction about me, I am a PhD student in from Indian Institute of Science, IISc Bangalore, and just to give a short overview of what I work on, I work in the area of molecular imaging. I primarily focus on synthesis of contrast agents for photoacoustic imaging. So here are some of the details I have given through um, such as my website. Here's my link for my website, and you can also reach out to me if you have any doubts for the course through the mail ID where I've mentioned it here. And in addition to that, if you have any other doubts related to the course, you can always reach out to me through the discussion forums. And just to go on further about this course, Optical Spectroscopy and Microscopy. So this is a 12-week course on NPTEL, and it's a postgraduate level course. So you'll all, like as I said for the past 2 weeks, you will be given weekly course material, and for all the course material, you will also always be assigned um, given assignments, so which you have to complete by the given deadline. And I think by now already your week 1 and week 2 deadlines are over so far, which is good in a way. And in addition to that, we'll always be having TA sessions, me as your TA, every Sunday from 3 p.m. to 5 p.m. And here's the link I've given here, the mentioned here, the link for the meeting where we'll be having the TA sessions. And if you guys have any doubts, you can always reach out to me through mail or through any of the discussion forums. And I checked the discussion forums. There are quite few doubts about the course as well as the how the course will be taught and what all the exams how is the pattern of the exams and all those stuff. Those are general doubts, I guess. But in case if you have any other technical doubts, please feel free to reach out to me and through either through the discussion forums or through my mail, and you can reach out to me. So what we'll be doing generally for all the TA sessions is the plan is simple. So briefly, I'll be going through a short recap of what happened. Um, Briefly, I'll be going through a short recap of what happened for the previous uh, and the previous week's lectures. So every week, as you can see, has 5 lecture modules which you have to go through, and you have to answer the assignments accordingly. So we'll just be going over the week's recaps. And from my part, what I'll be doing is I'll be preparing some sample questions for you guys, and which will be trying to solve. I'll also try to provide a variety of questions which might um, resemble the question exam pattern that may come for your exams, which will give you a brief idea of what kind of questions can you expect. And in addition to that, from this week onwards, we'll also be discussing the previous week's answers. So for this week, we'll be discussing um, week one's assignment answers. So let's get started. So this is the brief recap of whatever happened in the week's lectures. So before that, I wanted to ask if anyone has any doubts from the course, like from the previous 2 weeks' course content. Okay, so I guess no one has any um, doubts for as of now for the lecture. So I'll just get directly started with the uh, recap. So third week of the lecture for this course all depended on setting up a brief context for light matter interactions. In fact, the content for the past 3 weeks, right from week 1 till week 3, have focused on setting up a context. So I've focused on setting up a quantum mechanical context of how light interacts with matter and what comes out of it, and how do we measure these, how do we monitor these interactions, how can we express them mathematically, and how do we carry forward these mathematical expressions to study basic processes like absorbance or fluorescence or phosphorescence and so on, and how do we take use of these uh, physical processes to make instruments which we can use to study biological phenomena. So that was the basic um, idea behind the whole course. And this week's course content primarily focused on setting up the context for the initial part of the course, that is to study your radiative processes such as your absorbance and fluorescence. So the initial part of the lecture started by discussing the start. I wouldn't say started by discussing. It morely focused on expanding the concepts uh, from week 2, which focused on this time-dependent perturbation theory, which is TTPT, and it kind of tried to provide a what to say, I can say a rigorous quantum mechanical description of your transitions from your ground state to your excited state, as well as from your excited state back to your ground state. And most of these processes were kind of laid out briefly by Einstein, and it kind of provided what, as per the course instructor, it kind of provided a phenomenological way to balance the rates of light matter interaction. And all the processes that we saw so far, all the mathematical expressions that we saw so far in the lectures, focused on three main processes, which are this is your absorption, where your light energy pushes a molecule from the ground state to an excited state, and your stimulated emission, where your light energy stimulates excited molecule to drop down and emit a photon, and spontaneous emission, where a molecule kind of drops down naturally without needing an external light field. And we also saw a variety of mathematical expressions and derivations which primarily focuses on this Fermi's golden rule and this dipolar approximation. We saw a lot of conditions in which dipolar approximation can be made, and we saw a lot of conditions in which the Fermi's golden rule will stand, and what and all components do we need for calculating this Fermi's golden rule, such as your uh, matrix elements for the interactions, as well as your density of your fixed states. And we also, in the process of calculating this Fermi's golden rule, we also came across a lot of coefficients and derivations, where we saw a lot of factors like your BKG or BGK, which are tied to your molecular transition matrix elements for your absorption as well as your stimulated emission. And we also saw a key parameter called as AKG, which is a molecular rate constant for your spontaneous emission. And we also saw how AKG and factors like AKG and BKG are related to the frequency by a factor of your cube of a frequency, which is nu cube. And we kind of had an idea into seeing why spontaneous emission is much more significant at higher frequencies than at the lower frequencies. And towards the end of the lectures, we also saw more about the uh, Boltzmann's distributions, where we saw about the population of the photons at your ground state as well as your excited state. We also saw how, although the transition rates from the ground state to the excited state is similar to that of the excited state to the ground state, the population of the photons at either the ground state is much more higher than that of the excited state. So as a result, the transition rate the transition rate of the spontaneous emission can sometimes be neglected from the picture. And in the end, we also saw more about our first order rate equation for your fluorescence lifetime, as well as for your decay kinetics. And we also saw a lot of parameters, such as defining the lifetime of a molecule by using the rate constant of your rate constant, that is your EKG. And all of these factors put together, it gave us a brief introduction into the calculation of something called as the Beer-Lambert law, which is which gives a picture into how your light energy is how the absorption of certain molecules is calculated by a function of their path length, the concentration of the uh, chromophore of our choice, as well as external parameter called as the molarization coefficient. And we also saw how the molarization coefficient can be calculated through quantum mechanical manners. So this is the brief recap of what kind of uh, calculations and what kind of concepts we learnt in uh, week 3. Um, I kind of don't think I missed anything in the recap, except for I kind of missed a key important part, saying that we also went into calculating the constants, which highlight your uh, perturbed by Hamilton operator and the unperturbed Hamilton operator this thing. And I also kissed the uh, key factors or expressions that involve the dipolar approximation. And right now I am not focusing much on the mathematical expressions, since there might be some people um, who might not be having that much mathematical background. With those kind of stuff, you can um, I'm thinking, or I'm guessing that you can learn that if by having the course suggested book in your hand, or if you have an interest towards deriving those formulas. So without that, I think this is the uh, brief recap of what happened uh, in the week threes of week three lectures. So from here, what we'll do is we'll have a short doubt session till 3:30. So if you have any doubts conceptually by the till week three, we can shoot up till. So I think the time is 3:15 right now. So maybe till 3:20 we can have a short 3:20 or 3:25 we can have a short doubt session, and after that we can go on to discuss some of the problems in the lectures. Okay, if there are no doubts for now, we'll get started with. Okay, if there are no doubts for now, we'll just get started with the problems. So the first question given here is, what is the fundamental difference between stimulated emission and spontaneous emission? So we saw about two concepts in the week three's lectures. One is simulated emission and one is spontaneous emission. And we also saw a key difference between simulated emission and spontaneous emission. So there are four options here. It's an MCQ question. One is stimulated emission occurs without light, spontaneous requires light. Second option is stimulated emission depends on the radiation energy density, which is rho, spontaneous does not. So third is spontaneous emission produces two photons, stimulated produces one photon. There is no difference, they are the same process. That's the fourth option. So what will be the correct answer? So it's a bit of a tricky question because the concepts are kind of overlapping, but at the same time, there is a key difference between all these options that say separates the right option from the wrong one. So can anyone guess what is the correct option? If you can't open the if you can't open your mic to say the answer, please feel free to open the chat box and then tell the answer. Okay, we'll going over the answer. So the key difference is trying to looking at the options correctly. The correct answer is actually option number B. Stimulated emission depends on the radiation energy density rho, while spontaneous does not. So the key difference here lies between the accuracy of the answers. So we look at the options one by one. Stimulated emission occurs without light, spontaneous requires light. Because this is not right because it's just the opposite. Because spontaneous emission doesn't require light, whereas stimulated emission requires light. So as we saw in the previous slide, stimulated emission requires a light energy and then it will release two photons. So automatically this option, option C also doesn't hold valid because spontaneous emission will produce one photon on its own, while as simulated produces two photons. One is the photon that induces the stimulation, the other is the energy that is released when the photon de-excites from the relaxes back to the ground state. And they are not the same process, so this option doesn't also hold true. So the right answer is B, where stimulated emission depends on the radiation energy density, whereas spontaneous does not. And that's the reason it's called as a spontaneous emission. So let's move on to the next question. How does the rate of spontaneous emission, which is it's actually AKG, but I have written as A, scale with the frequency of the transition? So how does the rate of the spontaneous emission scale with the frequency of the transition? So four options are here. Once again, it's MCQ, inversely proportional, linear, proportional to V square, proportional to V cube. So which one of them is the correct answer? is a key question which arises out of Einstein's phenomenological approach to light, where your AKG depends on a lot of factors, and the expression is almost given by your 8 pi h by c cube. There is one more parameter missing, which is your frequency parameter, and you just have to find out with what power or what division of frequency does the AKG vary. It's a pretty theoretical question. Okay, so it's a direct question, so the answer is pretty straightforward. It is proportional to mu cube, which is your where mu is your frequency of the light energy. So we'll go on to the next problem if everyone's clear with this. So this is a pretty mathematical calculator problem. If a molecule has a spontaneous emission rate constant AKG is equal to 2 into 10 power 8 per second, what is this fluorescence lifetime? So the problem is pretty straightforward, but you need to apply the right formula to get the answer. So we have a molecule here. It has a spontaneous emission rate constant, which is AKG, which we all know, and the value is given by 2 into 10 power 8 per second. So we just have to find out what is its fluorescence lifetime, which is tau f. So the options are given by 5 nanosecond, 10 nanosecond, 2 nanosecond, and zero point 0.5 nanosecond. So what will be the form? So two things here is what will be the formula that you will be applying, and how do you calculate out the uh, fluorescence lifetime. So people can take out maybe probably 2 minutes till like 3:30 to solve this problem, and at 3:30 probably we'll start solving the problem. Okay, so we'll go on to discuss the answer. So the question is pretty simple. We have given the AKG and we have to directly calculate the fluorescence lifetime. So the relationship between AKG and tau f is simple. Um, okay, I didn't mention the. Okay, so the relationship between AKG and tau f is simple. So tau f is basically 1 by AKG. So we just have to find the reciprocal of this AKG to find the tau f. So tau f is basically 1 by AKG, which is 1 by 2 into 10 power 8. So which will give you, so it will just basically be 1 by 2, which is 0.5 into 10 power minus 8, which is basically 5 into 10 power minus 9 seconds, which is 5 nanoseconds. So I hope everyone is clear with the answer. So okay. So I'll proceed to go with the next question. So according to the first order decay equation, what percentage of the excited state population remains after exactly one lifetime? So the question says, according to the first order decay equation, what percentage of the excited state population remains after exactly one lifetime tau f? So the options are 50%, 0%, approximately 37%, and 100%. This is also a pretty theoretical question. So what will be the answer for this? So the answer for this is pretty straightforward, which is option C, which is approximately 37%, which is 1 by E, because it varies by E power minus 1. So we'll go on to the next question. What is the primary requirement for the dipole approximation to be valid? So what is the primary requirement for the dipole approximation to be valid? So the options are: the molecule must be larger than the wavelength of light, the wavelength of light must be much larger than the size of the molecule, the molecule must have a permanent magnetic moment, the light must be perfectly monochromatic. So once again, a theoretical straightforward question. It's an MCQ. So the answer is option 2, which is the wavelength of the light must be much larger than the size of the molecule. So only under these conditions the dipole approximation can be considered valid. So we'll go on to the next question. So the B coefficient in Einstein's treatment is directly related to which molecular property? So the B coefficient in Einstein's treatment is directly related to which molecular property? So the options given here are mass of nucleus, transition matrix element squared, melting point of the substance, and number of electrons into the shell, in the inner shell. Sorry. So which one of the options will hold true? Once again, it's a direct theoretical question. It's kind of related to your I think we have only discussed one of the options here in detail in so of the in the lecture so far. So only that option will kind of hold true. So the option answer is option B, which is your transition matrix element squared. I hope it's clear. So we'll move to the next question. If a molecule's transition dipole moment is perfectly orthogonal, that is sorry. If a molecule's transition dipole moment is perfectly orthogonal, that is 90 degrees to the polarization of the incident light, what is the transition probability? So this is also a very easy question. You kind of don't need a calculator for this. It's easy to calculate what this is. So if you understand the question correctly, a molecule's transition dipole moment is perfectly orthogonal to the polarization of the incident light. What is the transition probability? So the answer to this question can be solved if you know what happens to the polarization, what happens to the light when if it is a perfectly orthogonal filter, polarization filter. So the answer for this is 0, which is option C. So basically, if you are you have an orthogonal filter, polarization filter, and if you have an incident light, there is not going to be any resultant light coming out of that polarization filter polarizer. So it just means that the probability that it goes to the excited state in this case will be 0. So if this question is clear, I can go to the next question. So why is the fluorescence lifetime useful as a diagnostic tool? Why is this will be discussed in the last 5 minutes of the last lecture of week 3, I guess. So why is the fluorescence lifetime useful as a diagnostic tool? So the options are: it tells us the exact weight of the molecule. Second option is it is sensitive to the local environment and molecular interactions. The third option is it determines the color of the molecule under a microscope. The fourth option is it measures the speed of light in the sample. So for this theoretical question, so it's sensitive to the local environment and molecular interactions. That's why the fluorescence lifetime is useful as a diagnostic tool. At thermal equilibrium, so the next question, sorry. At thermal equilibrium, the ratio of the population in the excited state to the ground state is determined by. So we saw as per certain concept before the Einstein's phenomenological model, where someone decided a certain theory, and in that theory he kind of said why the emission from the why the transition from the excited state to the ground state can be neglected, and we came to saw that the ratio of the population in the excited state is very less compared to the ground state, although the rate of transitions from the ground state to the excited state is similar to that of the excited state to the ground state. So uh, what is this ratio determined by? So the options are Beer-Lambert law, Boltzmann distribution, uncertainty principle, and the size of the detector. So the answer is option B, the Boltzmann distribution. And we'll go to the last discussion problem for this week's lectures. So this is a problem which is kind of a numerical answer question, which I want you people to work it out. So in a the question goes as follows. So in a time-resolved fluorescence experiment, a sample of molecules is excited by a short pulse at t is equal to 0. The population of the excited state, which is n of t, follows an exponential decay. If it takes 30 nanoseconds for the excited state population to decrease to 13.5%, which is approximately 1 by e square of its initial value, determine the fluorescence lifetime of the molecule. So the question you kind of can see through the screen, I am presuming. So they are given a bunch of parameters where I have given nt and how much nt varies with respect to n naught after a certain amount of time period. So using that, you have to calculate how much the fluorescence lifetime of the molecule will be. It's a mathematical question. It's a formula based question. You have to solve and find out tau f, and this is a numerical answer question, so there will be a range of values for which tau f will be correct. But for now I'll just teach you how to solve the question probably. So you guys can take time till probably almost 3:45. I can try solving the question from probably 3:50. Okay, we'll try to solve the question. This has been like I think 10 minutes or something. Okay, so we have NT and we have the ratio of NT by N naught, and we have this expression here which signifies, which correlates NT to N naught. Basically, we know that the population of the excited state is given by the ground state into the correlation factor, which is e to the power minus a kg into t. And we kind of know here from the question how much is nt with respect to n0 after a certain time point. So we know that nt by n naught is equal to e to the power minus 2, because I have mentioned here that which is 13.5%, it's approximately 1 by e power 2. So nt by n naught is e power minus 2. So you plug in those values and then you plug in the time of t to 30 nanoseconds. So we kind of know that AKG. So if you calculate both of them, you will find out that minus AKG into T is equal to minus 2. So AKG into T will be 2. So you plug in the value of T here, which will be 30 nanoseconds. So you will get AKG is equal to 2 by 30, 2 by 30 nanoseconds. We are not calculating AKG directly now because we have to determine the fluorescence lifetime of the molecule. And from the past answer, we saw that the fluorescence lifetime of the molecule is given by 1 by AKG, which is now 30. So AKG is 2 by 30. So if you substitute here, you will get tau f, which is the fluorescence lifetime, will be 30 by 2 nanoseconds, which will be 15 nanoseconds. So the answer will be 15 nanoseconds. So this is how you will be solving a numerical answer type questions, where people will ask you to type the answer in nanoseconds, and you might have to type 15 as the answer. So I hope the answer is clear, how we got 15 as the answer. So usually what I do is I keep this as a doubt session, but since I already what to say spent gave a lot of time to solve the question as well this thing, so I'll skip this doubt session for now. So I'll directly go into discussing the um, questions for week one, the answers for the week one of the assignments, which we already know. So I'll just be going through very fast. Only if there are any problems, I will stop by the problem and then I'll kind of try to elaborate it in detail. So the first question in the week one assignment was momentum and localization of the particles in space are related by which principle in quantum mechanics? The question here is pretty straightforward. The answer is uncertainty principle, option A. Polarization of light can be measured using this was the second question. It was a multiple select question answer. So there can be multiple answers which can be correct. And the answer for this is we will be using both the you can use both the polarized and analyzer combination, or you can measure the absorption along with different axes. Sorry, angular distribution among the photon emitted electrons. So the options are both B and C are permitted questions or permitted answers. Okay. So the third question, the uncertainty principle is it's a multiple select question and answer again, and there are four options here, and once again the answer is options C and D, which is the uncertainty principle sets limits to accuracy and the uncertainty principle also determines the lower limits of precision in a measurement in a system. So the correct options are C and D. So the fourth question is, Dirac's formulation makes the size absolute, relative, invariant, and can be used as an absolute quantity. So the correct option here is option A, which is absolute. Okay, so this is a problem. So determine the uncertainty momentum of a particle of mass m whose position with respect to origin when measured is given by 400 plus or minus 10 nanometers. Given Planck's constant is 6.62 into 10 power minus 34 joules second. So, can anyone try to solve this problem in the class? How to do it, or should we just go on to the answer? So the simplest way to go around solving this answer is by directly using the Heisenberg's uncertainty principle, where we know that the product of the uncertainty in position as well as the momentum will be greater than or equal to your Planck's constant divided by 4 pi. So your delta x by delta, can take me laser pointer here. So your Heisenberg's uncertainty principle says that delta x into delta p is greater than or equal to h by 4 pi. So here we know that the uncertainty momentum is given by 400 plus or minus 10 nanometer. So out of this you have to take this 10 nanometers as the uncertainty momentum. So you have to plug this 10 nanometer in this delta x formula, and if it plug this in and then if you substitute here, dividing it by Planck's constant and multiplying it by 4 pi, you will get the uncertainty momentum, which will come around greater than or equal to minus 2.63 into 10 power minus 27. So the final answer will be greater than or equal to 2.63 into 10 to the power minus 27. The SI unit will be Newton meter. So the next question, PMT, which is your photomultiplier tube, proves that light has what kind of properties. So it is a multiple select question. So here they have four options. Out of that, we know that two options are correct. So the correct options are options A and C, which is that light consists of particles or photons, and photons have energy. So these two options are correct. So the next question, when a polarizer and an analyzer is kept at 90-degree angle, the ratio of the output intensity after the analyzer and input intensity of plane polarized light after the polarizer is given by. So this is also a multiple select question. So two answers are correct here, and since uh, like they have given only one question here, 90 degrees angle and a polarizer, so it's pretty easy to calculate the answer. So it should be either the cosine square of 90, or which fundamentally implies that the ratio will be 0. So both cosine square of 90 and 0 are appropriate answers. So you can give both of them. We'll go on to the move on to the next question. So using the mechanical shutter, the shortest light pulse that can be generated would be dash. And they're given that the laser of 683 nanometer with a bandwidth of 2 megahertz. This is also a MSQ question, so more than one option can be valid. So this is also a problem. So does anyone want to mention the formula that will be used to calculate the shortest light pulse given we have a bandwidth of 2 megahertz? Okay, so we'll proceed to discuss the answer. So we know that we know the formula of the bandwidth. We know the formula of relationship between the duration of the light pulse being generated and the bandwidth of the laser as this formula, where your one second, I'll just get the laser pointer, where your delta t represents the duration of the light pulse and your delta nu represents the bandwidth of the laser. So delta t is equal to 1 by 4 pi into delta nu. So where they have already given the bandwidth as 2 megahertz, so we just have to plug in the value of 2 megahertz, which is 2 into 10 power 6 hertz into this. So your delta t will be 1 by 4 pi into 2 into 10 power 6. So if you proceed to solve this, you will get delta t as approximately 4 into 10 power minus 8 seconds. And if you see across all of this options, you can see that it fits two options here. One option is that it's shorter than your 10 power minus 10 power minus 7 seconds. Your 4.4 into 10 power minus 8 seconds is shorter than 10 into minus 10 power minus 7 seconds, but it's slightly longer than 10 into 10 power minus 10 seconds as well. So both option A and D are correct. So the correct options are shorter than 10 power minus 7 seconds and longer than 10 power minus 10 seconds. So I'll go on to the next question. Um, if each diode inside the PMT, which is photon multiplier tube, were to emit 20 electrons for every electron detected, what would be the number of electrons reaching the anode for every electron originating at a photocathode. The PMT has 10 diodes. I'll repeat the question once again probably. If each diode inside the PMT were to emit 20 electrons for every electron detected, what would be the number of electrons reaching the anode for every electron originating at a photocathode? The PMT has 10 diodes. The options are 10 into 20 power 10, 10 into 20 power 20, 20 into 20 power 10, and 1 into 20 power 10. The answer is kind of pretty straightforward. So to discuss this, let's just say we have one electron. When the first electron strikes the first dynode, 20 electrons are going to come out of it. So I can probably touch a laser pointer. So on and so forth. So let's just say one electron strikes here. So out of this, 20 electrons are going to come out of it. So the number of electrons originating at this so the number of electrons originating from here will be 20 power 1, which because where 1 is the number of the dynode. So all these 20 electrons will be falling on the second dynode, and for each electron falling on the dynode, 20 other electrons will be falling out of it. So the number of electrons coming out of the second dynode will be 20 into 20, which is 20 power 2. And so it kind of follows a relationship where the number of electrons originating out of a photocathode is 20 power the number of diodes. So this will be 20 power 1, 20 power 2, 20 power 3, 20 power 4, so on and so forth. And they are saying that the PMT has 10 diodes. So it means that the total number of electrons originating and reaching the anode will be 20 power 10. And we have the option here as 20 power 10. So the correct answer will be 1 into 20 power 10. And the last question, the work function of a one second, I'll just take the work function of a photocathode. It's an MSQ. So we have to find out the work function of a photocathode. There are 4 options here. Measures how many electrons would be emitted for a given photon. Determines the potential energy of the emitted photoelectrons. Determines the minimum energy that a given photon should have to release a photoelectron, and determines the kinetic energy of the emitted photoelectrons. Which one of these is correct? So since it's a multiple select question, so there are multiple correct options to it. So the correct options are options C and D. So the photocathode determines the minimum energy that a given photon should have to release to a photoelectron, as well as it determines the kinetic energy of the emitted photoelectrons. the correct answers are option C and D. It's a theoretical question. So that's all the questions and answers for week one's assignments as well. So we have solved some sample problems in week 3 as well as we have come across some problems in week 1 as well. So the time now is for 4:10 I think. So till 5 the TA session is open. So we'll have a doubt session till the end of the session. So that's all the lectures for today. So if you have any open doubts which are very pressing, you can ask it here. Otherwise, I'll see you guys in the next session, which is on the 15th February Sunday from 3 p.m. to 5 p.m. So in the next week, I'll probably be discussing um, week four's recap along with sample problems from week 4, and in addition to that I'll also be discussing some of the weekly assignments of week 2 and week 3. So if you have any doubts, please feel free to ask those doubts. um, if not, please you can also feel free to leave the room if you don't have any doubts, so we can meet in the next Sunday. Thank you. Okay, if no other doubts are there, I'll see you on the next week in the week 4 on 15th February from 3 p.m. to 5 p.m. Thank you.